Once the amplitude y is known as a function of time, then of course you can draw a free body diagram and you can calculate everything because y is already known. When you're calculating everything to calculate internal forces or moments or shears, you're no longer using the M asterisk and the C asterisk. The M asterisk and C asterisk and K asterisk and P asterisk are used only to find the response y. Once y, capital Y, is known, then we go back to the original structure and we can compute from there, as I will show in the example. It's important to note, in case you look in books or in the internet and so on, that in theory, you could say that the moment at any point is the curvature times EI. And since we know that the curvature is the second derivative of the displacement, and we made an assumption for the displacements, there is a temptation to say, I don't need to look at free body diagram. I already know that the curvature should be phi double prime times y of t, and then that's the curvature, just multiply times EI, and that gives me the moment. And that would be true in theory. But the problem is this: the shape is maybe reasonable. Hopefully, the shape phi is reasonable. But how reasonable is the derivative of the shape? Maybe not so good. And how reasonable is the second derivative of the shape? Usually much, much worse. Okay? So, we avoid using derivatives of the shape to calculate anything. We only use the derivatives of the shape to calculate the coefficients of the single degree of freedom equation, but after that we don't appeal to them anymore. We use statics to calculate what's going on in the beam, and any questions hopefully will be clarified now in the example. So let's look at and conclude with a small example. Okay, so the example that we're going to use is a cantilever beam of length. We're going to use a system of units that is consistent. So I'm not saying whether it's feet or meters or something, except that taken care of, that's not going to fit. So we have a consistent system of units in which the length of the beam that we're looking at is 10.
You want to put L or 10?
No, L. We're going to start with symbols, and then after that we're going to substitute values for the symbols. That's it, I think, right?
Yeah.
So we have a beam, as you can see there, cantilever with a distributed load that varies as a function of time. We're not yet saying what is that function of time. That covers half the beam. There is a spring in the middle, K1. There is a dashpot at 3/4 of the length. There is a mass per unit length on the cantilever. Maybe we should draw that cantilever a little thicker because it looks like it's just a little line. Just draw a double line at least. So it does have a mass per unit length. It's not massless. So we have a cantilever with m bar per unit length, has an EI, which is also constant. It's subjected to a concentrated load PT. We're not saying what is the variation of the load. At the end of the beam, there is a concentrated mass M1 that has a rotational inertia J1. And we eventually will solve it for a specific case, but let's derive first what are the equivalent terms. So go ahead.
You have to guess the shape first, right?
Oh yes. We need to do the first step, which is to assume some shape to solve the problem, because this problem has infinite degrees of freedom because the beam is flexible. So let's take something easy. Let's assume that y is a function of, let's assume that the shape is x over L squared. That's really easy. Now this shape is okay in the sense that at x equal to 0, we see that it is 0. So we know that cantilever is held on the left side. At x equal to L is equal to 1. So we see that the capital Y that we would be using would represent actually the movement at the tip of the cantilever. And that's it. Okay. In addition to that, it's kind of nice in the sense that if I take a derivative of the shape, I'll get what? 2x over L squared, right? And at x, yeah, you can put the derivative if you want because you're going to use it. Yeah. So the derivative of the shape is going to be 2x over L squared. And the second derivative of the shape, maybe put it on the right side. In fact, all of them. The second derivative of the shape is going to be simply 2 over L squared. So if we look at this, the shape x over L squared looks like a reasonable shape for a cantilever that is loaded down. The derivative is 2x over L squared. At least at x equal to 0, it is 0, which is fine. That fits for a cantilever. So those are fine. Now if we look at the curvature is constant. It's 2 over L squared. That's not so reasonable, right? Because if you use EI times the curvature, that means that the moment diagram is a constant. So there is as much moment at the tip as there is at the root, which is, of course, at the tip is 0 and at the root is largest and so on. But it doesn't matter. As I said, we will not use, when we calculate internal effects, the derivatives. So now that we have that, let's plug into the formulas and see what is M asterisk, C asterisk, K asterisk, and P asterisk. Just write it down. Okay. I mean, they have the formula, so there's nothing to say other than M. That should be M, a small m. Let's use small m. The equivalent properties are all small, but the small letter with an asterisk on top. Now, in this case, we're integrating from 0 to L, the m bar. The phi squared is x over L to the 4th, the x, plus, now the mass M1, in this case, the phi is just 1, right? Because at where the mass M1 is located, if you substitute the phi, which is x over L, you can see that it's a 1, so it's 1 squared. Now, if you substitute, now you also have the j. So that's going to be plus J1 multiplied times the derivative of the phi at that location squared. Now let's look at the derivative of the phi. What is the derivative of the phi? No, previous one. Yeah. So at x equal to L is 2 over L, and so 2 over L squared. Okay, so that's our M asterisk. Now the C asterisk is the same formula, except in this case, we don't have any C bar, so there's no integral.
Yeah, 0.
We don't have any distributed dampers. We only have one concentrated damper, which is C1, and that damper goes times the phi at the 3/4 of the location squared. To know what is the phi at the 3/4, you just put 3/4 for x, you will get 3/4 squared, which is 9/16, or 3/4 squared if you want. That's fine, just write 3/4 squared. That's it. So that's C asterisk. The next constant is K asterisk. That's the integral of EI times the second derivative squared, which is 2 over L squared times dx plus the concentrated springs. In this case we have only one, which is K1 multiplied times the value of the phi at that point squared. In the middle, the phi is going to be 1/4, and so I mean it's 1/2. No, wait, x over L. No.
Yeah. L over 2 over L, which is 1 over 2 squared. Yeah.
No. Yes. No. No. It's K. The formula is
yeah.
K times
Yeah.
phi squared.
Yeah.
So the phi is 1/4.
Yeah.
The phi is 1/4,
Yeah.
but the phi goes squared.
But the K is at L over 2.
Right. So the K is at L over 2. So what is the phi at L over 2? It's not 1/2, right?
Yeah.
It's
Yeah.
1/4.
Yeah.
So the phi is 1/4,
Yeah.
and the phi goes squared. So it's 1/4 squared. Because the formula for K asterisk is K times phi squared.
Yeah.
And the phi is 1/4.
That's correct.
And that's it for the stiffness. Except, okay, yeah, that's it for the stiffness.
We need
Except, well, you didn't integrate the mass.
Yeah.
It's just obvious from looking that it's equal to m bar L over 5 plus m1 plus 4 over L squared J1. Now integrate the K bar, I mean the C bar is just, doesn't have to do anything, that's 9/16 of C1. And this one is 4 over L to the 4th times EI actually, and then it's going to be times L, so it's over L cubed plus K1 over 16. And then now we have the load, and the equivalent load P asterisk is the integral of over the structure of the distributed loads. In this case, the load is acting from 0 to L over 2, so it's WT from 0 to L over 2 multiplied times phi of x, which is x over L squared dx, plus the load PT multiplied times the phi at that location, and that's 1. And there's no more loads, and there are no concentrated moments, so let's do that integral. That's going to be WT times L over, no wait, oh yeah, because we are integrating from L over 2. So it turns out that when you do the integral, you get WT L over 24 plus PT. So now that we have those things, in the corner over there, just write what the numerical values for, we won't finish the whole thing with the numbers, but let's just put the numerical values there. It'll be easy. We made one error, I think, when we were putting the numbers, right?
Yeah.
So let's say L is 10, M bar is 0.1, J1 is 4, M1 is 0.2. It's hard to see the point in the 0.2. No, it's fine. Just C1 is
0.5. EI is
and EI is
100,000.
100,000.
K1 is 400. WT is 2.4 step. And PT is 2 step.
Now we made an error on the K1 or something when we were,
Yeah.
So we had K1 over 4 or something?
Yeah, we had K1 over 4.
Okay, so you can say that instead of K1 being 400 is 100? So to get the same numbers you had? Because you divided K1
Yeah, so-
over 4 to get 100, right?
We need it 4 times
Oh no,
bigger.
1600, right?
Yes, we need it 4 times bigger. Because we had it K1 over 4.
But it should be over 16.
Yeah, so we...
So that means you can make it 4 times bigger.
Yeah. and we get
So
the
if we
same.
make, so let's make, we're gonna change K1 to avoid an error to 1600. Excuse me, I got a call. Hello? Yep, I'm ready. Okay. Bye. So, with those numbers, erase everything except the beam. The equation of motion
So do you want the numbers for M star?
No, just write the equation of motion at the end. Once you get M star, okay, fine. If you want to, yeah, that's okay.
Numbers?
Yeah, the numbers.
And PT.
Okay, so these are the numbers. So the equation of motion. No, numbers.
Oh, maybe on the numbers, like.
Put it in a box. Okay, so this is the equation of motion once we've reduced it to a single degree of freedom system. Now erase the numbers on the left side here and just let's remember the most important thing, which is that we said that y, erase those two. The thing to keep in mind is we said that y as a function, little y as a function of x and t is equal, we said it approximately equal because in this case our approximation is that this is equal to x over L squared times y of t. And so under that assumption and substituting in the appropriate formulas, we obtain that the equation of motion for the system is the one in the box. Now, because what's on the right side is a step, that means that we can solve this equation as if it's for a step load, right? It will depend on the initial conditions, and it will depend on nothing. Well, for example, what is the frequency of this structure, omega? So omega for this structure, our best approximation for this model is simply square root of k over m. So it's equal to and if we want to know what is the ratio of critical damping of this structure, we have to calculate C critical. And therefore the ratio of critical damping, the fraction of critical damping that we have turns out to be 0.84% of 0.0084. Okay, now let's say we wanted to do this equation. I'm not going to do it, we had it in mind, but it's gotten taken too long. So we're just going to say, if I wanted to solve that equation, I would say it would have what? Let's say exact. That equation would be what? It would have a homogeneous and a particular solution. The particular solution would be a constant, because the right hand side is a constant, right?
Yeah.
So let's write the particular solution. We're not going to complete it, but let's just say let's say that y of t total first. Y of t is equal to y of t particular plus y, I usually put it on the top instead of on the bottom.
Here?
Yeah. Plus y of t homogeneous. So there is a particular solution, there is a homogeneous solution. The homogeneous solution is always the same. E to the minus I omega t, A cosine omega t, B cosine omega t. The particular solution depends on the right hand side, and for a case of a step is just a constant. So if we take it as far as seeing what is that constant, so let's say the particular solution is equal to D. So substituting D into the equation, what do we find? Two derivatives of D is 0, one derivative of D is 0, so we have 500 times D is equal to 3, and therefore we find D to be 3 over 500, which is 0.006. So now we know, now let's write the total solution in terms of constants, and we already know psi and we already know omega, so just put the number. So y as a function of time is equal to to D, which is the particular solution, 0.006, plus e to the minus psi omega t, which is e to, in this case, minus 0.25, I think.
Yeah.
T times a cosine omega damped, and in
Omega
this
damped is close to
in this case omega damped and omega are essentially the same thing, because the damping is so small. So we're just going to write it the same. So it's 29.88 T plus another constant times the sine of 29.88 T. So that is the solution. Put it in a box. And let's erase everything else except that box and the upper box. Okay, so we had that system. That system led to that single degree of freedom equation, and the solution of that single degree of freedom equation is this. Now, if somebody asks me, what is the time history? I'm going to ask first a simple question. First, before, what is A and B? Well, A and B are going to depend on the initial conditions, right? We know what y of t is. So it's going to depend on initial conditions, right? If the beam is starting from rest, then we would say that let's not solve for the conditions, for the initial conditions. But if we know the initial conditions, that y, for example, is 0 at 0, and y dot is 0 at 0, or y dot is 1 at 0, or y dot is 5 at 0, it doesn't matter. We need two conditions that will allow us to calculate the constants A and B. Once those constants are computed, then we finished. In the sense of the response is that y of t. Now, let us assume that we've already done that, and that we have solved for A and for B by substituting into the initial conditions. Okay? Now let's say that the question is, calculate the time history of the moment at x equals 3/4 of L. Hello. Okay, bye. Okay, so we want to calculate the moment at the 3/4 of the length. Now, at this point, if I want to calculate the moment, show where that point is with a bubble. So that would be a free body diagram cutting at 3/4 of the length, right? If you wanted to calculate the moment there, you would take a look, for example, at that free body diagram. And that's it, right? Now that doesn't matter if it was static or dynamics or something. If you want the moment there, that's where you cut. So in this case, the free body diagram would involve, at the point where you made the cut, you have a moment, which is what the question is, mt. You also have a shear and an axial force. So that moment is mt. You have a shear and you have an axial. There is an applied load, P of t, and what else is missing? We have the inertia forces, which are missing. Now, the mass M1, draw it underneath it because there's space. Just put the load going up under the mass. So that load going up is equal to M1 multiplied times its acceleration. But what is the acceleration of that point? Is y double dot times phi at that location, right? But the phi at that location is 1. Therefore, that is the inertia of that thing. In addition to that, that point has a rotational inertia. So the mass is rotating clockwise because that's the way we had the phi. Therefore, we have a counterclockwise inertial moment, which is equal to J1 multiplied times the rotational acceleration at that point. Now, everything is proportional to y. Now, the angle at that point is phi prime, right? It's the derivative of phi with respect to x. Now, we could repeat phi prime. Phi was, write it on the side. Phi was x over L squared. So phi prime was what? Was 2x over L squared. No, just 2x. So phi prime at the end of the beam is 2 over L. Therefore, that's J1 times 2 over L, which is the angle, times y double dot. because 2 over L times y double dot is the rotational acceleration at that point. It's the angular position times y double dot. At that point, if I want mt, I just sum moments, and that's it. Okay? You have values for m1, you have values for j1, you have values for pt, you have value for everything. And y double dot, of course, would require that you take a derivative of the equation that you see in that box, right? Once the a and b were known. Okay, so I will probably make an effort, see if I can fabricate an assignment for you so you can work it out during this coming week. All right, bye.